Hey class, so this is the video on the homomorphism section here. We all kind of know what homomorphisms are at this point, so just a quick definition, right? If I have a phi going from a ring to another ring, right? Phi is a homomorphism if it preserves the algebraic structure, right? That's all there is to it. Now, it's actually important to think about what we mean by algebraic structure. So officially, a ring has a plus, a times, and a 0. Officially, it does not have a 1, right? So we don't have to preserve the 1. Even if it has a unit, it doesn't have to preserve the 1. And that's going to be important for an example in just a bit. So of course, what you need to have happen here is you need phi of 0 to be 0, right? And here I'm going to go ahead and leave out the, phi of 0r has to be 0s, right? Phi of r plus s in the sense of r has to be equal to phi of r plus phi of s. This is in the sense of s, right? So if I were to decorate things, it'd be like that. Same with multiplication. Phi of r s is equal to phi of r phi s, right? And let's see, and do I need no, I guess I don't. Yeah, so this is an important point, right? I don't actually need to add that. So we do have a group, right? So we do have additive inverses. We might or might not have some multiplicative inverses, but I don't have to mention it specifically. But we actually get that for free here because if I have an additive inverse, right, then I have phi of r plus. Let's be a little bit careful here, right? So what does it mean to be an additive inverse? So I have r and r, right? And I have s and r with the property that r plus s equals 0. That's it, right? This time, because we have commutativity, I don't have to worry about both sides. In Morpho, we show that this is the unique thing that satisfies this. There's only one of these things, right? So here I'm going to have phi of r plus s. So assume I have the additive inverse. Well, I know that this is phi of r plus phi of s, right? But I know also that this is 0, right? So this is phi of 0, right? And so this is equal to 0. Everything over here is sort of, these things are on the r side. These things are sort of going on the s side, right? But the point is that this is equal to 0, right? But what does that tell me? It tells me that phi of r plus phi of s is equal to 0, right? But this tells me then that phi of s is in fact minus phi of r, right? So additive inverses are preserved, right? The same thing will happen. It's useful to know this, right? So if it is the case that r and s both have a unit, right? Actually, let's think about a couple of things. So if r and s are unitary, and phi of 1 of r, I'll just write it once, right, equals 1 of s, right? So it actually moves the unit to the unit. Then the same argument I just gave up there will say that phi moves multiplicative inverses to multiplicative inverses, right? So if we have a 1, right, and u is in ur, right, then the inverse, then u inverse, right, is, again, the unique say s, such that us equals 1 of r, right? So I have here that phi of us is phi of 1, right? And we say this is 1 of s, right? But it's also phi of u, phi of s. That's because products are preserved, right? But this tells me then that phi of s is equal to phi of u minus 1. Again, just using the fact that if we have inverses, they're unique. So as long as I preserve the multiplicative identity, I automatically preserve inverses as long as I preserve the the additive identity. I automatically preserve additive inverses, right? Those are important things to remember. One last thing is this. So it's definitely the case, and we're going to see an example. So if phi, say going for, oops, sorry about this, I'm making a mess. If phi, okay, if phi going from R to S is a homomorphism, you know what, there's actually, let me just introduce some notation so I have to keep writing this thing. So I can just say is in hom RS, right? If I needed to make it even more clear, I could say in ring homomorphisms, right? And you know, one R exists, so there's a unit in R. Notice it doesn't have to be the case that there's a unit in S. Let's see, I didn't actually think of an example of this, but I guess let's see. Let me come back and think about an example. I think I know an easy one. But what I want to point out here is even if there is a 1 in S, it doesn't have to be the case that phi maps 1 to 1, right? So that doesn't have to be the case. So it is not necessary that, by the way, if I misspell things, sorry, phi of 1R equals 1S, right? What do we know? I mean, so this is going to be important later. So what do we know? Let's say phi of 1 is equal to S in S, okay? What we do know is this. We know that phi of 1 times 1 is the same as, so we know it's the same as two things. We know it's the same as phi of 1 times phi of 1, and we know it's the same as phi of 1, right? Because 1 times 1 is 1, right? So in particular, phi of 1 is S. What we have here is S times S equals S, right? So we have S squared equals S. Okay, so when we have an element such that S squared equals S, we call that element idempotent. Let me just make sure I have the right word. Yep, idempotent. Okay, it's going to come up in an example. So idempotent. Okay, so even if we have a homomorphism which is not a homomorphism that fixes ones, if it happens to be the case, let's see, sorry. No, yeah. So, I mean, so we have a homomorphism that doesn't care about what ones are, right? It just happens to be the case that R has a 1. And then whatever phi of that 1 is has to be idempotent. That's what we know. So we don't know it has to be 1, right? So if it turns out to be the case that the only idempotent element in S is 1, then we know that phi of 1 is 1, right? But sometimes it will turn out that that's not the case. So for example, the only idempotent, so if we have phi going from say, well, let's do it like this, from say, from R to say Z, right? Okay, so suppose we have that. Well, the only idempotent, and say that this is a ring with unit, right? So the only idempotent, 1 in Z is the only element satisfying x squared equals x, right? That's the only one in the integers, right? So any homomorphism at all, as long as there's a unit here, will have to map the 1 to 1 because the only idempotent in Z is 1, right? So that's an example there, right? But there are other rings where there are many idempotents, and so we'll look at an example of that in just a minute. I think that's all I wanted to say. Let's see. I did all that. Okay, yeah. So actually, yeah, I want to look at this example now. All right. So we did an example like this for groups on the exam, right? So here I'm asking the same question, like when is it the case that we can have a map Z12 to Z28? right? Nothing special about 12 and 28. Like, what is a condition, right? So what conditions? So phi is a homomorphism, right? What conditions must be met? So here I'm just asking what necessary conditions are there, right? To show that they're sufficient, we'd have to actually produce homomorphisms, right? So there'd be a little bit more work. You did this with groups, right? So we kind of know this. We know that if so, just looking at the group structure, right? How do we do this? We know that we know it must be the case that phi of you know, first of all, everything's determined by where phi of 1 goes, right? So I guess that's kind of the main thing, right? Because wherever phi of 1 goes, this is a cyclic group. So um, I mean, both are cyclic groups, right? But the point is that this whole thing's generated by 1, right? So once I know where phi of 1 goes, I know where everything else goes, because because phi of whatever 3, right, will be phi of 1 plus phi of 1 plus phi of 1, right? There's no options. Like, once you know where that goes, it's like we had in vector spaces. Like, once we knew where the basis goes, we know where everything else goes. Once we know where generators go, we know where everything else goes, right? So 1 is a generator. That's the point here. And what we knew, so say this is some k, right? So now this is in Z28. The property we had to have was that phi of 12, right, which is 12k. Sorry, 12k, right? But 12 is the same as 0, right? So so it's got to go to 0, right? Because phi of 0 has to be 0. So this has to equal 0 mod 28, right? So our condition then was that 28 has to divide 12k, right? So that was the condition. In general, right, the what we looked at was like if we had z of zm. Now I'm just looking at the group structure at the moment, right? Zm to zn. The property we had to have was that if phi of 1 is k, right, we had to have that n divide km, right? That was the property we had. So that's the same property here. Now here we can simplify this a little bit, right? So I can divide up by 4, and so I have 7 must divide 3k, right? And so so I must be the case that 7 divides k, right? And so we must look over here and just figure out what things are divisible by sorry, k is on the 28 side. So which things less than 28 are divisible by 7, right? And so 0 is, you can't forget 0, 7, 14, right, and 21, right? Yep, that's it. Okay, right. So those are the possibilities. In fact, this is just this subgroup, right? Oops, subgroup generated by 7, right? And in fact, we know that we could generate, if we're just looking at the groups, right? We know that we have 4 different homomorphisms here. One just maps everything to 0, so that's kind of silly. But the other maps 1 to 7 and 1 to 14 and 1 to 21, right? Those are our options there, right? So that's on the group structure, right? So what did we just add about the ring structure? We also need to know that phi of 1, which is our k here, is idempotent, right? So we could have done the opposite thing and just said, let's look at Z28 and look for all idempotent elements first. But we can sort of restrict this down in 2 ways. Now we can look at this and say which things are idempotent, right? So 0 is clearly, 0 squared is clearly 0, right? So yep, check, right? So let's just go through this list, right? 7 squared is 49. So what is 49 mod 28, right? So it's like 21. I guess it's 21, right? Okay, so that's out, right? Because we need 7 squared to be 7, right? Okay, well, what is 14 squared? So 14 squared. Oh my gosh. So let's see. Let me see if I can play with some algebra here. So this is actually 7 squared times 4 squared. All right. So we decided that's actually just, I'm doing everything mod 28, right? So 7 squared turned out to be 21. So this is 21 times 4 squared, which is 16. Let's leave it 4 squared for a second. And so this is, sorry, I know I could just pick up a calculator and do this. So this is like 7 divides here, 7 divides there, so 24. That's, and 7 times 4 is 28. So this is actually 0, right? So this is equal to 0. Okay. Maybe we'll come back and check that in a bit, right? But let's try 21. Okay, so 21 squared, right? So what do we get when we do 21 squared? So again, this is 7 squared and 3 squared, right? And so to get somewhere with this, 7 squared was the same as 21, right? So this is 21 times 3 squared. So 3 times 3. So 21 times 3 is 63. Okay. How many times does 28 go into 63? So that's 56 is 2 28s, right? And so we're looking at a difference of 7. I'm getting nervous, right? Okay, so these two things multiply together give me 56, and that's equal to 7 mod 28, and then 7 times 3 is equal to 21. Yay! Okay, so there's another one, right? Okay, so we got that. So here's our two, 0 and 21, right? So the two homomorphisms we can make are going to be where we map 1 to 0, and this of course just maps everything, right? So this is just the map phi. Going from Z12 to Z28, which just sends everything to 0, right? So the kernel of phi is actually all of Z12, right? And phi 1 equal 21, right? So that's the other one. So phi 1 equals 21 is the other one, right? And let's see, and you could go and figure out what the kernel is for this thing. Let's see, what would I do to that? Which things get sent to 0? I don't know. Maybe I just have to figure it out. I don't want to think about it too much. Let's see. I mean, phi of, let's just figure out what a couple of things are. So what is phi of 2, right? So it's going to be 42, right? So mod 28. Gosh, I'm so bad with algebra. I mean, so bad with arithmetic. 28, right? So if I take 12 and subtract 8, I get 4. Leaves me with 14, right? So this is actually 14, right? And then phi of 3, right, is 21 times 14, right? And so that turned into, 7 times 7 times 3 times 7 times 2, right? And the, let's see, the two 7s turned into 21 again, so this is 21 times 3 times 2. Okay, 21 times 3 was 63. We just did that one a minute ago, right? 63. Oh, but then, yeah, 63. So it was 7, right? So this is 7 times 2. If I did that right, so I'm getting 14 again. That seems strange. Anyway, you get the idea. We could figure it out. Actually, let's just do this. This is kind of fun. Let me just do this a silly way. Here. All right, so here's a little spreadsheet. Why not? Ancient technology at this point. So what do I want to do? I'm looking at 1, 2, 3, 4, right? All these up through 12. Actually, maybe I wanted to start with, no, up to 11, right? I actually want to start with 0 here. And here I'm just looking at equal to, so mod, I think this is how we do it. This times 21, 28. Okay, of course that's 0, right? So we can pull it down. Okay, so then we get that. All right, so we get 21, 14, 7. I messed that up somewhere, right? Then we get 0, right? So 4 is in the kernel, 8 is in the kernel, right? So the kernel of this thing, so phi going from Z12 to Z28, and we have the kernel of phi is equal to the generated by 4, right? And so this is just 0, 4, and 8, right? And we have then that, I mean, I'm just writing out everything, right? So Z12 over 4, right, is isomorphic to whatever the range is. So the image, I guess I haven't actually stated that yet, but we'll have that. And this group has size 4, right? So this is this ring has size 4, right? So whatever this ring is, so it's a subgroup of size 4 that's sitting in there, right? A subring of size 4 that's sitting in there. And I guess we computed it. Let's see, what is it? So it's 0, 7, 14, and 21, right? So it's actually that. So it's actually that, and so this is actually equal to this, right? Sitting inside of Z28. Good. All right. So I mean, we've analyzed this to death, right? But that's the way we do it. It was a good example to sort of look through. One thing I wanted to point out is if we were looking at homomorphisms in the category of unitary rings, right, so that the ones had to be preserved, right, then there is no homomorphism, right, because there is no map from Z12 to Z28 that can map 1 to 1, right? That can't happen. Okay, so just sort of keep that in mind. Is it the case that there's a unit in this, right? I mean, that's another question, right? So if we look at this thing itself, let's see. So 7. What do we get? 7 times. 7 times 7 was 21, right? Which is not there. 7 times 14. Let's just actually do this sheet again, right? Let's just do this, right? So let's have 7. Let's just do it by, so equals mod 7 times 14, 28. So that's 14, right? 7 times 7 mod 28, right? If I didn't screw it up, was 21. Yeah, okay. And then 7 times 21, okay, what is that? Mod 28 is 7. Oh, okay, so 7 times 21 is 17. Let's see, 14 times 21 is 14. Oh, there we go, right? So 14 times, or 21 times 21, right? It's 21. So just to be clear, this image has a unit, right? So sitting inside of Z28, right? As a subring, right? So the image is always a subring, is actually a unitary ring, right? Where the unit isn't 1, where the unit is now 21, right? So the unit is 21. So anyway, that's interesting, right? So now I think we've analyzed it to death. I can't think of anything else to say about it. Good. So I guess in some sense, right, if we look at this part of the map, the homomorphism does map 1 to 1 because it's mapping 1 to 21, but not the one of this thing, right? So it's not. So in that sense, it wouldn't be a homomorphism of unitary rings into Z28, but it is a homomorphism of unitary rings into the ring generated by 7, right? So I don't know, it's interesting. One last thing to talk about, and we actually kind of use it up here, is this first, second, and third isomorphism theorem. The first one's kind of the thing that proves the other, so that's actually by far the most important one. In the picture, it kind of says everything, right? So if we have a homomorphism, R to S, right, then one thing it says is if we look at the kernel, and we look at R mod the kernel, so what is this map? So this map is R gets mapped, so anything in here gets mapped to R plus the kernel. Okay, so that's definitely a homomorphism. And then there's a natural way to extend this homomorphism up. So let's call this natural homomorphism here. I'll call it psi, and I'll call this extended thing phi hat. Okay. And how does phi hat work? So phi hat of something here, which is like r plus curve phi, is going to be phi of r, right? Like that. So that's the way the map will work, right? So we say this commutes, right? Because this says that phi hat composed with psi, right, equals phi, right? So so it's called a commuting diagram because if I go this way, I do the same thing as I would if I went that way. Lots and lots of algebraic theorems can be written by drawing pictures like this and saying it commutes, right? And that's it. That's the whole argument. So anyway, I mean, this is important. Just to be careful. I mean, something I guess I haven't really said is, it's always the case when you have a homomorphism, right? That the kernel of phi is a ideal, right? So that's easy to prove, easy to show. I'm going to say that's an exercise. The image of phi. And by the way, remember an ideal is also a subring, right? The image of phi is a subring of S, right? So that's always going to be the case. This map here, right? I mean, maybe that's the thing to say here is that this is actually an isomorphism, right? So this is a bijection, right? So phi hat is actually an isomorphism of R curve phi isomorphic to the image of phi, right? So that's important. Okay. So there. Yeah, that's it anyway. I think that's okay. So that's the first isomorphism theorem, right? And yeah, I drew the picture and said it commutes and said that's the first isomorphism theorem. That's literally true, right? That's what it is. And then and we use that all the time. I mean, we will use this a bunch and surprisingly often. I mean, it's used a lot in group theory too. We just didn't use it that much, but in ring theory we'll actually use it a lot. The second isomorphism theorem is sort of interesting. So it says this thing: if I is an ideal in R and S is a subring, right? So the picture is like this: I have I subset of S subset of R, right? Then I can form S plus I. So this is the ring formed by taking the sum. So if you don't know what that means yet, that's what our next video's on. So maybe just wait for that. But basically, it's just the sum of terms from S and I. And then, so if I take, so it's a subring of R, that'll be a subring of R. And if I divide out by I, then I get that that's isomorphic to S itself over I intersect S. Okay. Also, when you take an ideal and you intersect it down, you get another ideal, right? Now we need this inclusion in order for this to be true, right? Things need to be sitting in that order. I guess a special case of this is when R equals I plus S, right? And then we get R over I is actually isomorphic to S over I intersect S. So that's an important subcase of this, right? And the way this works is simply to define phi going from S plus I to S mod I intersect S. So I guess one thing you need to do is you do need to show that's an ideal, but that's clear, right? I mean, this intersection of two subrings is a subring, and the fact that this is closed under multiplying on the left and right by R will get us back into here, right? I mean, so we'll get back into I, and so so that'll. Sorry, I'm only wanting to show it's ideal in S, right? So if I multiply on both sides by S, well, multiplying by S and S doesn't matter, but multiplying I and S will get me back into let's see. Okay, sorry. Let's see. So I'm taking something in S. We got to think about this for a second. In S, and I'm saying that I want to know that S I intersect S is still contained in I intersect S. That's what I want to know, right? Yeah. Okay. Oh, yeah. Sure. Right. So if I take something in here, right? So that's like some S prime.